Now knowing the derivatives of trigonometric functions, let's do some examples. Okay, so first example is just differentiating some normal-ish functions. And so if we differentiate this, we want to find g prime with respect to theta. And so here, as we look at this thing, first we recognize there's a product, right? So then we have to do the product rule. There's 1, and here's our second function. So I would do 1, and then d2 derivative of tangent is secant squared theta, and then derivative of theta with respect to theta is 1. And then I would do plus 2 tangent of theta minus theta, and then times the derivative of e to the theta is just e to the theta. Okay, and if you really want, you could rewrite this. This is the same thing as tangent squared. It really doesn't matter, but there we go. Try the derivative of this function over here on your own. And here you go. Okay. Now, yeah, I recognize that in the second piece here, the second expression here is a difference of squares. So you could FOIL it out, and it probably simplifies nicely. Somehow, I'm just going to leave it as is. For now, if you were to use this derivative for something, say to find a tangent line or something, then I might worry about simplifying it. But otherwise, honestly, leaving it just as is would be perfect. Okay. All right. Next, we're going to look at some limits. Okay, this is fun. I see, so limit as x goes to 0, and then I have sine, right? And remember that in the back of our brain, right, we're remembering that if we have the limit as like theta goes to 0 of sine of theta over theta, that was 1. Okay, so I'm going to try and use that as much as possible. So what I'm going to do, limit as x goes to 0, let's see, so I'm going to break this up. It'd be sine of 3x, and then times sine of 5x. And there's an x, yeah, okay. But then I need a 5 under this one, and I need a 3 under this one. Okay, well then I need to multiply by 3, right, to make sure I'm multiplying by 1, I'm not changing the value, and then also multiply by 5. That'll work. Okay, so then here I get limit. Actually, I can pull the 3 and 5 out, so I'd have 15 times the limit as x goes to 0. And then I know these limits exist, right? The angle matches the denominator. That's what this is saying. So then I can break it up. I can do limit of sine of 3x over 3x times limit as x goes to 0 of sine of 5x over 5x. And both of these are just 1, so I get 15 times 1, also known as just 15. Okay, there we go. See if you can manipulate this next limit with this limit identity. And here's my answer. So first thing I did was divide everything by theta, which is actually the same as multiplying by like theta over theta and then just rearranging. And so if I did that, right, I got sine theta over theta plus tangent of theta over theta. And then I simplified theta over theta is 1, and then tangent theta, right, is sine over cosine. So I just wrote it as sine of theta over theta times 1 over cosine theta. And then as I look at this, I can distribute to each piece. Numerator exists. I know that's 1. Denominator, okay, 1 is 1. Limit of that is 1. And then sine of theta over theta, that exists, and that's 1. And then also 1 over cosine as theta goes to 0, that's still 1. So all of those exist, and I just have 1 over 1 plus 1, so 1 over 2. Done. Okay. Next example, okay? We have a function, we need to find the equation of tangent line. Okay, so tangent line, we know we have to find the derivative, and the derivative evaluated at the point is our slope. Yeah? Okay, so we do 2 minus secant squared of x. And then I have to evaluate this at x is equal to 0, right? And secant of 0 is 1, and so square that is still 1, so I just get 1. Okay. And then if I look at f of 0, just find our point, because I need a point and a slope to find a line, and so f of 0 is just going to give me 0. Okay, and so then in all, my tangent line is just y minus, okay, is the y coordinate of the point, is equal to slope times x minus that. Or this is actually nice, just y is equal to x. Look at that, kind of fun, okay? And our last example is with more of a physical context. Okay, so then here we go, or here we are with an elastic band. It's hung on a hook, and mass is hung, and so it's stretching down, it's pulling downwards, and then it's released, and it's going to vibrate vertically with this displacement function, S. Okay. And so we want to find the velocity and acceleration functions. Velocity is just so the velocity function is the derivative of the displacement function. And so we just have to do the derivative. This would be, let's see, -2 sine t plus 3 cosine t. Okay. And then the acceleration is just going to be the derivative of velocity. So then derivative of sine is cosine, positive, but then I have a -2 out in front. Derivative of cosine is minus sine, and I have to keep the coefficient in front. Okay, that's fine. All right, next question. When is speed the greatest, right? When is speed the greatest? So speed, technically that's related to velocity. So we're looking at the velocity function. We want to find where it peaks, and we find where it's peaking by looking when the derivative of that function is 0. Okay, and so that's really the acceleration function. So I would set the acceleration function -2 cosine t minus 3 sine t equal to 0. Okay, rearrange it. So I'm going to write it as 3 sine t. So really I'm moving the sine over, but then I'm switching sides, so this side is still -2 cosine of t. And so then if I divide it by cosine and move the 3 over, I would get tangent of t is equal to -2/3. Okay, and so then t, if I solve for t here, I would get, arctangent of -2/3, and then have to add on a multiple of the period. Okay. And so those are the locations when the speed is greatest. And so we really should check. And what we would have to do to check, we'd compare the velocity function and the derivative velocity, the acceleration function. And we'd have to look at, arctangent of -2/3, check on either side of it, do like, v of, I have no idea what this is as a number. I'm just going to do like v prime of -2, and I'm going to do v prime of 0. I'm just guessing. And then what we would need to see for greatest, right, is that this number, whatever we pick for our test values, gives a positive value for that derivative and a negative value for 0. And so we'd see the increasing and decreasing behavior for velocity, and thus we get a maximum. Okay, so some applications of the derivatives of trigonometric functions. Okay, as we go forward, we're going to look now at derivatives of composite functions.